So, welcome to the 22nd session of Artificial Intelligence. As I said, this will not be a live session, but only a recorded session. So, for those of you who are accustomed to see me in the lecture hall, this is something a little bit different, but not too much. Okay, today's topic is data log. Data log is kind of application of Prolog principles to database management systems. And we just start with a look at conventional databases. Databases are an extremely important application of computer technology in nearly every part of where computers are used. For example, the very first letter you get when you get born in Germany as a new citizen is your tax identification number, which is of course stored in a central database where for every citizen of Germany there is a recording of such a number. At the University of Osnabrück, for example, we have the registration office where for each student there is information about the name and the address and the course of study and the matricle numbers generated there, of course, and so on. In the examination office, we have any information about examinations and the question of what kind of successful elements in the study have been completed by the students and what's left to do, and so on. And for example, in StudIP, we have the courses, we have the course enrollments, we have the learning material, so the content, we have a lot of communication data like the internal messages and the forum entries and so on. But even your browser has a database to store the cookies, to store the history, the bookmarks, so nearly everywhere. If we think of really large databases, there's more such things like the Google search index. Can be seen as one large database where for every web page in the world there is an entry of which words appear on that page, and this can be retrieved and use the Google search engine to find information on the web. Or for example, the Facebook database contains data about person, about connections between persons, the status updates you do, the pictures you upload, and so on. So from very small to really, really big databases, there's a large variety in nearly every part of what we do with computers. If you look from the other side, from the product side, we can say that our first product programs actually were databases. So we put family facts in our product programs to say, for example, Tobias is a male and has some children, and so on and so on. And then we can have simple queries like, tell me whom is Tobias a father of, for example. And we get all the X for which this relation is true. We have seen that product programs can be arbitrarily large, so there's no limit, like the program can have at most 10,000 lines or 1 gigabyte or whatever. Basically, only the memory is the limit that you have in your computer. Prolog databases, we've seen that can be modified dynamically. We can add new entries via assert. We can delete entries via retract and abolish. And if we combine both, we can update entries. And we can read entries by the queries. So we have the typical create, read, update, delete operations that are performed on databases, and we can do this in Prolog too. We know that the queries can be arbitrarily complex. Since Prolog is a full programming language, this means that we can do any kind of computation in our queries that is computable by computers. So arbitrarily complex. That means in principle we could use Prolog as a database management system. And if you look back at the list of databases, the question is Prolog a suitable system to do these tasks, to manage these data? For example, the cookie storage in your browser, the StudIP database, or the examination office database, or the Google search index database. And question is Prolog a good idea for that? to answer that question, we have to take a look at how Prolog works with these databases. Everything Prolog uses as facts and rules has to be in random access memory. Drawback is that this data is destroyed when the computer crashes, when we have a power failure, when someone turns off the computer, and so on. So it's not reliable memory. To have reliable or persistent memory, we have to have some kind of file system, for example, in Prolog, where we can consult our files from, or we can save the programs to. QSave program is a predicate that saves the current state of the Prolog program, including all the facts and so on, into a file. And so this could be a way to make the data persistent. But we have to load the data in the memory to be able to work with it, and have to save it back to make it persistent. This is very slow, and perhaps this can't be done for every single write operation. Let's look at some figures for StudRP, for example. The StudRP database at the University of Osnabrück has an entire size of 18 gigabyte without the uploaded files. That's another terabyte, but only the data on who are the persons, which seminars and lectures do we have, who's enrolled in which lecture, who has written an email to whom, and what's part of this internal message, and so on. We have about 1.1 million read operations per hour on the StudRP database. That makes an average 300 per second, and that's an average value. That means average including the night and the holidays and so on. In peak times, this can be 10 or 20 or 30 times higher than that. That's the read operations. The write operations are far lower, only 15,000 per hour, or 4.2 per second, but that's still a lot. So if you think about writing the database back to disk after each write operation, this isn't feasible. We've got a traffic of about 1 megabyte per second from and to the database, summed up. So it's not possible to write the entire database to the file system after each write operation. We could say, we only do this for parts of the database, only the part of that have changed. But again, this would be very difficult. And there are tables that are updated quite often. So this isn't a good idea. And this means, that's not surprising, of course, that for larger databases, at least a dedicated database management system is needed. And it must have some kind of efficient persistency strategies. So how to ensure that the data is persistent, that it's consistent, that can be queried quite fast, and so on. And the typical methodology that's in use for that is relational databases. Relational databases are kind of de facto standard for databases since they've been invented in 1970. Most of the database management systems you encounter are relational database systems. The largest one, for example, the open source scene are MySQL, PostgreSQL, MariaDB, and so on. Of course, there are others. There are NoSQL databases that do not use this relational scheme, but we stick to this relational scheme now. The idea behind these relational databases is that data is stored as relations using tables. What does that mean? A table, for example, this table is called student, contains the student relation. That is, for each student we store an ID. No, this is just a number here. We store a name, for example, a username and a matricle number. Also, Tobias Thielen has a username T. Thielen. The matricle is 998877, and the ID is 1. So for every person, there's one row in this table, and we have as many rows as we have persons. For example, in the tax identification database, we would have 80 million rows, since we have 80 million people in Germany, for example. And that's not a problem for such a relational database management system to have very large tables. The largest tables in Stutterby database, for example, have about 1 million rows. And that's not a problem. Okay, now we would like to store the course of study. Of course, since it's a student database, we don't only want to have the name, the metrical number, but also the course of study. So we could put a string in here, like Tobias Thielen is studying Bachelor Cognitive Science. Jan Meyer is doing the same. Martina Müller, for example, is studying Bachelor 2 subjects, Latin and Philosophy. Then we have a Master of Cognitive Science and a guest in Cognitive Science, and so on. What strikes us here is that we have some kind of redundancy. So we have the same string multiple times here, and typically this kind of redundancy is unwanted and should be avoided in relational databases. That's because it's difficult to change. So if it's renamed, for example, if it's in some kind of unforeseen manner to be changed, then it's difficult because we have to do it in every place where it appears. It's error prone. If we have a typo like Cognitive Science without a C or whatever, then it's no longer considered to be the same. It uses much space, strings, it's 40, 50 characters and so on. And what one typically does is database normalization to remove such redundancies from the table representations. And this is done in the following way. We introduce a second table. The second table is called, for example, courses of study. And in this second table, we have all the different values of course of study with an ID. So the Bachelor in Cognitive Science has the ID 1, the Master in Cognitive Science has the ID 3, and so on and so on. And now in the original students table, we only include the IDs of the courses of study. So one points to this table and says Tobias Thielen studies BA in Cognitive Science, and so on and so on. We could have more information here. We could model the information in a more complex way to split away the bachelor from the subject and so on. In reality, this is even more complex since people don't only study one course of study, but perhaps several ones, and we need a more complex structure here. So this is just for educational purposes, just to show you how this typically works. And this is not a course on relational database design, but on logic programming. But we'll see that there are a lot of differences and similarities and some differences between these relational databases and product programs. So now if I have such a database, I can now query and manipulate it in a way. For that, there's a language called SQL or SQL, Structured Query Language, which is virtually standard for every relational database. SQL is standardized, at least to some extent. So these constructions like select star from students will probably work in every relational database, and we can have a look at such a database. Every one of you has a relational database in their browser, for example, and most of these browsers use SQLite. SQLite is a very simple SQL database, and for example here I have installed a Firefox extension called SQLite Manager, where you can look at the Firefox databases but also manage own databases. And here I have the student table. In the student table, you see the structure here has an ID, a name, a metrical number, course of study, and a username. And I included our 5 students. And now I can use SQL to say give me all the students, for example. And now I get back the table. If I replace a star by, for example, a column name, then I get the names of all the students. Okay, this isn't so exciting and surprising. If I want to have the names of all cognitive science students or bachelor cognitive science students in our database, for example, I can include a condition. Conditions are expressed with a where keyword. To say where course of study equals 1. Then I get just two names, Tobias Thiel, Michaela Meyer, who have the course of study 1. Okay, but this is not so elegant, because now I have to know what the ID of Bachelor Cognitive Science is, and I have the information in my database. And this is where combining tables comes in. And this is the SQL query. We'll go through that one in a second. When I say, okay, I don't only want to include information from the table students, but also the table courses of study. Then I join these tables. Joining means I make one larger table out of two tables. Typically I have as many rows as the left table has, so I get as many rows as the students table has, and information from the courses of study table is added, but I must tell the system on how to identify the fields that belong together. And I say, okay, this course of study ID from the student table should equal the ID from the courses of study table. So that is the criterion to join rows from both tables. And I say, okay, we are courses of study dot name. So the name of the course of study should equal BA in. It's a little bit difficult. In cognitive science. There was a mistake, because it says that name is ambiguous. We have a column called name in both tables, and I have to tell them which table I mean. And these are the names of students that study cognitive science, BA cognitive science, in our example database. And I identified the course of study by the name by combining information from two tables. And that's a very typical thing in SQL. You have queries that combine information from various tables. Like Prolog, SQL is declarative. So you see, we don't tell the database system how to construct these results, how to pick these and that and so on, but just like somewhat declarative description about how our results should look like. It's non-deterministic in the sense that we don't get one answer, but a list of answers, or so to speak, many answers. And we can use SQL not to create all the answers at once. This can be very dangerous if there are many answers. But to limit it, for example, to just one, and then give me the next, and give me the next, and give me the next. The same thing as we know from Prolog. But as a difference to Prolog, SQL is not based on logic, on predicate logic or whatever, but on something called relational algebra. So it has a sound theoretical foundation too, but a different one. And you'll learn about relational algebra and anything of relational databases in the computer science database course if you're interested. So if we now look at this database and the queries we had, we can easily do the same in Prolog. So our Prolog program would look like this one. A table in the relational database is a predicate in Prolog, A table row is a clause of the predicate, and a table column is an argument position of predicate. So we have a column, for example, of name in our students table, and Prolog doesn't support any kind of named parameters. Parameters are only identified by their position. So the name position is the second position in our argument list of the student's predicate. I prepared that in Prolog. Here we are. So these are our students, and these are our courses of study. The identical information that we've seen in the SQL database, and now we, for example, want to have all the information about all students. Then we have to make up some variable names. We could choose the name of the columns for these variables, of course. Then we get some kind of informative feedback. Course of study, choose an abbreviation. So okay, we have Tobias Thelen, course of study is 1, username is Thelen, and so on and so on and so on. I can get all these. If I only want to have the name, that was the second SQL query we had, I could choose anonymous variables for these values. Oh, I wanted to have the name, not the username. And then, as you know, I only get the names. Great. So now I want to have the cognitive science, bachelor cognitive science student. I could include the one here. So it's more true than in SQL. I don't have a where clause. I can just use unification to put in the values I want. And the other thing, I want to use the ID, course of study ID, and I have a second goal. Courses of study with the same ID, and the name of this course of study is BA in Cognitive Science, and I get both names again. And if I don't want to have this course ID, then I can use an underscore and so on. So you see, we can do exactly the same things like in SQL with our Prolog code. And this is really a strong structural similarity of how to work with these kind of databases. It's both declarative, it's both non-deterministic. Syntax, of course, is different, and the way to construct these queries is different. But on the other hand, it's quite similar. But of course there's a but. As you know, Prolog isn't used as a database system in large scale. SQL has one major difference to Prolog I haven't mentioned so far. To be efficient, the database query or manipulation languages are typically restricted in expressive power. So that means SQL is not a Turing-complete programming language. You can't write arbitrary programs in SQL. You can only do some things concerning your database. Prolog is a Turing-complete programming language, so there are things you can do in Prolog, but not in SQL. On the other hand, SQL databases can deal with large amount of data in a very efficient way. Prolog cannot. We've seen that. So the question now is, can we transport some of Prolog's expressive power? We've seen a lot of interesting applications of logic and Prolog to relational databases without losing the efficiency advantages. So databases are only interesting because they can efficiently handle large amount of data. And this is where Datalog comes in. Datalog is a kind of database query and manipulation language that extends relational databases to deductive databases. So what does deductive database mean? We can make inferences, deductions in our database, and use them for queries. Also, for example, if we want to deduce that students are enrolled in certain courses and certain courses belong to certain modules and parts of courses of study, and so we can use this kind of deduction and make a predicate finished all compulsory courses or whatever, and do this kind of deduction in our database as part of the database code. Datalog has a syntax that is a subset of Prolog. Unfortunately, it does show many different variants. So if you have two Datalog implementations, they will most likely not have the same syntax. They work on relational databases, that means tables, and Prolog-like rules. So we have this kind of table-based relational database, and we have rules that pretty much look like Prolog rules to access this database. Since it's similar to Prolog, the query evaluation, of course, here too is based on first-order logic, and it does so in a sound and complete way, and can be done even efficiently for large databases. And we have to look at some details on the next slides to explain why this can be the case and what the consequences are. Datalog is decidable. Well, you know, first order logic is not, so there are some restrictions. Usually it's done using bottom-up strategies. We talked like about unit resolution in one sentence last week. Unit resolution is a different kind of resolution strategy where we choose one fact that eliminates one goal from a list of goals and makes the clauses shorter, for example. What's the differences to Prolog? First have a look at it, and then we have to prove that something interesting can be done with this. We can't have complex terms as arguments of predicates. So anything like compound complex terms are disallowed. We only can have non-complex arguments, and this means we don't have lists. Lists, you remember, are complex terms in the way that they're eternally built with an operator and always have a first argument that's the first element of the list and a second argument that's the rest of the list. So we can't have lists. And Datalog imposes certain stratification restrictions. We'll talk about what this means on the use of negation and recursion. So negation and recursion are in some way restricted. And the restriction has a name, stratification. And the last one is that only range-restricted variables are allowed. So variables can be very free, and something might happen with them, but they're restricted to the range of values that comes from the database. And to achieve that, each variable in the conclusion of a rule, so on the right-hand side, left-hand side, sorry, the left-hand side in Prolog, it's written the other way around, must also appear in a not negated sub-goal of this rule. So if we have a variable somewhere in the head, this variable also have to appear in the body of the rule and explicitly in a sub-goal that is not negated. Each variable that occurs in a negated subgoal must also occur in not negated subgoal. So we cannot have free variables in our negated subgoals. Okay, the syntax is very similar to Prolog. The rules look like, we have a rule name, we have arguments u1 to un, and then we have subgoals r1 to rk with arguments, and some of these subrules are negated. So u are variables or atomic value, nothing complex. Every variable must occur in a non-negated body literal. So the variables here, u1 to un, must appear somewhere here, and these variables too must appear somewhere here in these rules. Okay, a Datalog program P is a finite set of rules. That applies to every programming languages. Programs have to be of finite length. And if a relation Ri only occurs in the body, not in a head somewhere in the program, then it's an extensional database relation. So, for example, if we have our grandfather relation, we say grandfather, X is the grandfather of Z if X is the father of some Y and Y is the father of that. Then father has no rules. Well, there's not a rule when someone is the father of someone else, but that's a fact in the database. And here it's included in our relational database. And the father would be a kind of relation that only occurs in the body. If a relation Ri occurs in at least one head, if you have at least one rule, for example, for grandfather, then it's called an intensional database relation. Extensional because it relates to the extensionally given facts, and intensional because it's derivable from rules, so to speak. Okay, predicates are either extensional or intensional. We cannot mix this. Okay, that's what we said a second ago. Only in the body, and it's extensional. In the head, then it's intensional. So this is a data log example. Here we have the facts that are in the database. They would be in some kind of table form, but we can include them in this way. As we've seen in relational databases, these are tables. We have 4 tables: father, mother, female, and male. Data log, these are extensional predicates, and in logic we could call these ground facts. We don't have any variables here, and we have no complex arguments, so you cannot put variables in the facts in the database, only instantiated atomic values, like we've seen in the students database some minutes before. There haven't been any variables or complex things. Okay, then we have rules. These rules perfectly look like Prolog rules. As I said, there might be some variance in syntax, but basically it's nearly the same as Prolog rules. Grandfather, grandmother, brother, and ancestor. The only thing that's kind of different here is the unequal predicate. We have seen that we can use negation in standard Prolog, where we say if they're not unifiable, then they are unequal. This is not possible here. We have to use some kind of unequality predicate. So in database terminology, we would call these relational operations, for example, given by queries. Typically, they are not part of the database itself, but a kind of part of the queries we have. Data log, we would call them intensional predicates, and in logic, as you see, it's implication. We only have restricted variables here. You remember that variables must occur in a non-negated body and so on. We don't have complex arguments, but we see that recursion is allowed. So we have recursion here in our ancestor predicate. That's allowed. There is some kind of recursion concept in SQL, or at least in some extensions of SQL, but it's not very commonly used. And but if it's present, it's the same kind of recursion as we see here in Datalog. So this is a direct influence from Datalog or Prolog to SQL. So if we have these clauses, we can ask ourselves which of these clauses are not in Datalog, are not allowed in Datalog. Equal and different must be built in. So we cannot have this kind of predicate because unification doesn't work in the same way as in Prolog, and we cannot just say, okay, we have two variables here that don't occur anywhere else and so on. This is not possible. This is not possible too. You cannot have this kind of negation. We will see why in a few minutes. Okay, this is possible to just switch arguments and have another predicate, the same thing here. This is possible too since it's a fact, and this is not possible because by only doing this kind of recursion, it's not allowed, and we will see why. Okay. We can have one look of a real example. So we can put this code into a Datalog interpreter. There's an online interpreter that you can use. Link is given here. I prepared that in my browser. So here we have our code. Looks like a normal Prolog program. Some facts, some rules. Just strict replies, and we have some queries. Who's grandfather of whom, who's brother of whom, and then who's ancestor of whom. And when we say execute, it generates all the answers. Yeah, that's basically it. We have this question mark after the queries, but on the other way, it just works like we've seen. We can put Andrew in here. You see this works too. Just like normal Prolog queries, basically. Okay. This is just an example of how syntax might look different. There's another online Datalog demonstrator that you can use with this kind of code. Here we have the variables prefixed with a question mark, and we have quoted all the atoms and so on, but still it very much looks like Prolog program. There are other variants of Datalog, especially Datomic, which does no longer look like Prolog, but basically has the same principles. Okay. So now let's look at the semantics of what happens there. And there's one very important concept that will be introduced now. Let's say we have a Datalog program P, and this program does not use negation. So we're first looking at programs without negation. We can define something we could call immediate consequence operator. So what is an immediate consequence operator? It transforms a set of facts to a new set of facts. So basically it's kind of extending the facts by using the rules. That's the idea behind this immediate consequence operator. It's called TP, and we say TP of F. F is a set of facts. TP of F is the old F, and builds a set union with some derived facts. These derived facts we could call H theta. You remember the theta operator is, stood for the variable substitution, for example, given by unification. It's the same here. It's some H with variables substituted. And the H comes from the rules of our program. So this is a Prolog rule or Datalog rule. No? So H if B1 to Bn. Part of P. P is the program. And every Bi theta should be part of F. So we pick a fact, apply variable substitution, and then this should be some of the sub-goals. That means all these sub-goals immediately refer to our facts. And there are no sub-goals that call another rule or need another rule or whatever. They only rely directly to the facts plus variable substitution, of course. So we get new facts that are in one step derivable from the old facts. One step, no? Only because these B1 to Bn must rely to facts, not to other rules. Of course, we get facts for the rule predicates. For example, we have a rule predicate that says someone is someone's brother if they are male and have the same father. Male and father are predicates from our database. So being a brother of someone else is something that will be derived in one step. And then we have new facts, new entries to the database that belong to the brother relation. And now if we have other rules that rely on brother, they can now make use of these derived facts. Before they couldn't be used because the brother rule in the body only referred to another rule, not a fact. So if we now iterate these one-step immediate consequence operators, like TP of F0, then we get F1 in new set of facts. We use this operator on F1, then we get F2, and so on. So step for step for step for step, we apply this operator. If we do this, then under certain condition, the sequence converges. It converges to a fixed point, and a fixed point means that if we go on applying this operator, nothing will change. So that's this condition here, fixed point TP of F0 is the same, stays the same when we apply TP. So the fixed point of TP of 0 is TP applied, and F0 is the starting point. And we call this starting point I, the set of all extensions of extensional database predicates, the ground facts. So the given facts are F0 OI. Okay, now we have this immediate consequence operator and the very important concept of fixed points. That means we apply the rules as long as there are still changes, so to speak. Okay, this fixed point of a function is a very general concept. Now, so there is an element x of a with f of x is x, and this is true for all the elements. Then we have a fixed point. And there's the Knester-Tarski theorem that says if A is a complete lattice, you know, lattice is a kind of graph with an infimum and a supremum, so one upper point and a lower point for every two elements from this lattice. Then there exists at least a least and a greatest fixed point. So we have two of them. Okay, we're looking for the least one. The special case for Datalog is that TP has a fixed point f, and f is reachable by applying TP iteratively to I finitely many times. So in Datalog, every admissible program has this kind of fixed point, and we can reach this fixed point with finitely many steps. So f is the least fixed point of this TP. The consequence of this is that f is a model of P from formal semantics. Model means that we have values for all the variables and facts and relations that fulfill all the rules given in the program. F is a model of P in the sense of propositional logic. And there, as you know, models are given by the set of true ground facts, so just a set of facts here. Let's look at an example. This is the database we start with. Father, John is father of Mary, Bill is father of John, Fred is father of Jane, and so on and so on and so on. And now we do the first immediate transformation step. And we'll derive some additional information, for example, that John is grandfather of Andrew. Since the grandfather rule only had two subrules for father and father, and it takes the information here given in the father predicates to derive these grandfather information. They're not recursive, so everything can be done in one step. Then we have this parent relation. We say, okay, two person are parents of the other ones if they are have the same child. And we have the ancestor relation, which has a recursive and a non-recursive rule. We at first get the ones that can be applied in one step without using the recursive rule. We cannot use the recursive rule because we cannot, that's okay, go away. We cannot use the recursive rule because the sub-goals in the rules have to refer to facts, and we don't have any facts for ancestor. After this F1 step, we do have facts for ancestor, and now the recursive rule can work, and can in the next step, derive all the ancestors that are 2 steps away. And has some additional brother information, because now we have more ancestor information, father information, and so on. And now in the next step we can derive the ancestors that are 3 steps away. Now, there's still new ancestor information coming in, Bill and Anne. So and after that nothing changes anymore. So all the recursive rules have reached their maximum extent. There are no more ancestors, nothing changes, and we have reached the fixed point after 3 steps. So and that is what Datalog does here when executing or calculating these information. Goes through step for step for step until the fixed point is reached and the entire list of data is there. So in a way we don't have a kind of real recursion like you would have in a programming language, where you have another call stack and a frame on that stack and so on. It's more like exploring the facts using these body rules and relating to them. Okay, that was the easy part without negation. So now if we introduce negation, we of course want to do it in a sound way, and the idea here is to use stratification. What does stratification mean? A stratum is a kind of a level, or in German you would say Schicht. We kind of seen that idea in the non-negated case just seconds ago, where we say, okay, the rules, the facts that are derivable in 1 step are on the first stratum, those that are derivable in 2 steps are on the second stratum, 3 steps are on the third stratum, and so on. So this stepwise growing of the database and so on, this is the idea of strata. And basically the same is applied for negation here. The idea is we do not allow recursion through negation. So that's not possible. We can only have negation of other predicates. So some kind of, we count the negations we encountered in the derivation process. In stratum 0 we have only derivations without negation. Then we have derivations with at most 1 negation, and so on and so on. And we say the semantic of these negated goals is that not P is true at stratum K if P is false at stratum K minus 1. We'll look at that in an example now. Let's go back to our famous 8 puzzle. We have this starting state and we have these intermediate states, and the question is, we want to write a predicate that says, is the state space connected? So can we go from here to here by some way? Okay. And let's look at this problem for a dependency graph. We say 2 nodes in the graphs are connected if there is an edge between them. Edge will be an extension predicate, so in our database we have these edge information, and we say there's a recursive case, there's a parentheses too much, something is connected if there is an edge to somewhere, and this somewhere is connected to our y. We've seen exactly that in the example before, where we say, okay, by finding a fixed point we get all these connected things. Now we want to have a predicate not connected. Not connected, x and y is true if x and y connected is false. So if the idea of connection between, the relation of connection between x and y is not included in the list of all the connections, then not connected x and y should be true. Okay, we said that these variables here must appear somewhere in the body, otherwise it's not admissible. So we introduce two rules, source x and target y, who just pick one of these two from the Edge database, and we can include them. So we have a restricted value for these variables here, and then it's okay for Datalog. And then we can have a predicate is connected x. That means a node x is connected to the rest of the graph in some way, and there we have a negation not connected. Okay, that's just the predicates. Let's now have a look at how they can be proven by Datalog. We say for the Datalog program P there exists a stratification. The stratification looks like Stn goes to Pn. Pn is a set of predicate names of P. So for the number of a stratum 0, 1, 2, 3 or whatever, we get a set of predicate names. It looks very strange at first, but we see how this works. In such a way that if we have states P and Q, then the stratum of P should be larger or equal than the stratum of Q if P is reachable from Q in the dependency graph and the P and Q path is marked with a minus. So this is the case here and here. So what does a stratification mean? We can say, for example, the stratum of the connected predicate is 0. Because the connected predicate is already available on the very first stratum with the number 0. It only relies to extensional predicates or some recursion, but not to negation. The same is true for source and target. They are also on the 0 stratum because they do not include any negation. The not connected predicate has one instance of negation, so this is located on the stratum 1, and is connected is located on the stratum 2, because only after applying negation 2 times this can be calculated. Because we say the truth value of a negated value is derived from the truth value of the non-negated goal in a lower stratum. Okay. We have a Datalog program P, and we now define a sequence of immediate consequence operators TPS, which basically does the same as our TP before, but now is able to include negation. We say the T of P and S of a set of rules F is of course the old set of rules. Build a set union with some new rules with variable substitution. These new rules come from our program P. The stratum of this rule should be S. So we put in here S when we start with 0. So at first we only get the rules from stratum 0. The subtargets with various substitution should be an F. So, you know, these non-negated goals must be immediately derivable from our database, just like in the example before. And now our negated subgoals can only occur if S is larger than 0, of course. Should not be element of the facts and of our program of stratus -1. So they should be only reachable in our current stratum S, but not in any strata before. So this is this selects all the rules that are reachable on this stratum. Okay. So now the fixed point is the fixed point of TPS, which occurs to the program at a lower stratum, if s is larger than 0, or it starts at I, of course. So we begin with the ground facts. We have a fixed point operator to find a fixed point for the first stratum. This is the way we went for the predicate before. So now we go on. Now we include all the predicates that have one negation. We have a new fixed point operator. We apply the rules again, including this new predicate now, and we include another predicate that's on the second level, and so on and so on and so on. So the example would be, first we start this one is an I. Then our first application, our first fixed point for applying these rules, even recursively, is this one. Then we include the not connected thing. The not connected thing can now look at these connected facts. And we don't have a fact saying B is connected with B. So not connected, BB is true, AE is true, BE is true, and so on. And in the second part, we have a new fixed point operator, including now the predicate is connected. And we again search for let it run until it finds a fixed point, and then we're done. So A, B, and D are connected to other nodes, and C is not, for example. This does not always work. And this is where the point comes in, that we must not allow recursion through negation. We have this extremely interesting application where we say someone might like beer or wine. We have two facts: John likes beer, Mary likes wine. And we have the additional thing here that we know that someone likes wine if this person does not like beer. We need some kind of additional goal here, because the variables have to occur in a non-negated body clause, subgoal. And we have the human being predicate here, fact here, that tells us that John, Mary, and Jane are human beings. And normally we should be able to derive that Jane likes wine because Jane does not like beer. But this does not work because we cannot make any stratification. Of course, likes, human being, and likes are available on stratum 0. But we cannot say that this likes isn't true, it's the same as here. We cannot say that likes is available on the stratum 1 because likes is not available in the stratum below. And we have to refer to the stratum below to find the non-negated facts. And so in this case we cannot do stratification, and this is not a possible Datalog program, though it is possible in Prolog. So if we add, for example, that someone likes beer if he or she does not like wine, this doesn't make it better. Same thing here if we include the beer or wine in the predicate name to make it two different predicates. But there are models for this, of course. Now we can find values that make it true. Again, this isn't true. We could ask what is semantics of P. P is some kind of X is connected to Y, but Y is not P. So this could be the case that we say P X is some kind of dead end. Those things go there, but there's no way back or so whatever. Again, this is not true because we have recursion through negation, and this is not possible. Okay, the fragment, because Datalog is some kind of fragment of the Prolog language, is decidable because all Datalog programs terminate. This is not guaranteed for Prolog programs, as you know. The Datalog programs terminate because we have this stratification and this idea in the fixed point semantics. The The statements and predicates can be stated in any order because we explore all the possibilities, and as we explore all the possibilities, it doesn't matter if in what order we do that. There are some methods that are really able to efficiently perform queries for that. So you actually can use Datalog as a query language for relational databases. It's not Turing complete in contrast to Prolog, but there are many really interesting applications of Datalog and related database query languages built on Prolog and Logic, built-in extension of databases, especially in semantic web context. Semantic web means understanding the World Wide Web, the web pages that are out there, not only as information for human beings, but also as information for computers. For example, if you search in Google, I told you that in the first session, other flights from Münster, Osnabrück to Munich, for example, then Google is able to present you a table where this information is included in a way that is not directly taken from the web pages, that it was able to detect this information and do inferencing. And this inferencing can be done as part of the database representation if we have a Datalog language for the database. Okay, there's a link to a manual if you're interested in more about it. We can actually extend the least fixed point semantics to some kind of Horn logic with function. Then we have Prolog. But then, as a drawback, the models may not be finite, and the universe of the things, the facts we need may not be finite too. So this restriction in Datalog is in a way necessary to have the advantages we need. Efficiency and guaranteed termination. Okay, that was quite a condensed lecture, but you can go back and listen to parts again, and we didn't have any discussion and any peer instruction questions, of course. That was it for today. In the next session, we look at some other derivations of Prolog, like F-logic, answer set programming, adaptive logic, and so on. But today we looked at Datalog, a very interesting application of a variant of Prolog for databases to make deductive databases in an efficient way out of relational databases. So, I say goodbye.